You know when you're following an argument, and it takes so many weird twists and turns that you totally lose the main point? Well, believe it or not, that exact same problem happens in formal logic. But logicians, they have a secret weapon, a really powerful idea for just cutting through all that noise. And today, we're diving right into it, the normalization procedure.
See, when we're building a logical proof, what we're really doing is forging a path from our starting assumptions to a conclusion. But is it always the most direct path? A lot of the time, nope, not even close. Proofs can have all these detours and unnecessary steps that make a simple truth look incredibly complicated.
And that's exactly where normalization comes in. Think of it as a procedure that just systematically carves away every single redundant piece of an argument until all that's left is the essential direct path. It's all about finding the very core of a logical deduction.
Okay, so let's start with the problem itself. Because in the world of logic, not all proofs are created equal, not by a long shot.
Think of it like this. You've got someone telling a story. A really good storyteller, they get right to the point. But a bad one, they go off on all these tangents, they repeat themselves. Well, a logical proof can do the exact same thing. And these redundant steps, these logical tangents, they can completely hide the actual point of the argument.
So, how do we fix this whole mess? We use the normalization procedure. It's a process that refines an argument down to its absolute purest form.
And here's what we're aiming for. On one side, you have a non-normal proof, which is like a tangled ball of yarn. It's full of these logical detours that make it indirect and just plain hard to follow. Our goal is to turn it into a normal proof, the most direct, essential version of that argument, with zero detours.
And this perfected, super clean version of a proof, it actually has a special name, the canonical form. You can think of it as the gold standard, the single best way to represent that logical argument. So normalization is really just the step-by-step process we use to get any proof into this ideal, crystal clear state.
All right, so let's get into the nitty-gritty. How exactly do we remove all these detours without, breaking the logic?
The main technique is something called detour conversion, and it targets a very specific kind of redundancy. So in logic, you've got introduction rules that let you build up a complex idea. Then you have elimination rules that let you break it down to use its parts. A detour is simply when you build something up, only to immediately break it down in the very next step.
My absolute favorite way to think about this is with a recipe. Imagine the recipe tells you to add a cup of flour. And then, the very next instruction is to scoop that same cup of flour right back out. What was the point of that? It was a completely useless step. Well, that's a logical detour. And this is the basic anatomy of that detour. It's a two-step loop that goes absolutely nowhere. You apply a rule to introduce some idea, and then you immediately apply the matching rule to eliminate it. Sure, the proof is longer now, but you've accomplished literally nothing. So the job of the normalization procedure, it's actually pretty simple. It just scans the proof, finds these useless introduce then eliminate loops, and just snips them out. It reconnects the argument directly and makes the whole thing way more efficient. Now, I know what you might be thinking. This all sounds incredibly abstract, right? But this is where it gets amazing. This purely logical idea has a direct, and I mean profound, connection to the device you are watching this on right now. So yeah, let's just ask the question. Why does any of this matter outside of a logic textbook? What on earth is the real-world application here? Well, the answer is hiding inside your computer's processor. This right here is one of the most beautiful and, frankly, mind-blowing ideas in all of computer science. It's called the Curry Howard Isomorphism. It shows a direct one-to-one link between logic and computing. So a proof? That is a program. A logical redundancy, our little detour, that is just a piece of inefficient code. And here's the kicker. The act of normalization, of simplifying a proof, it is mathematically the exact same thing as a computer executing a program. Running your code is literally a process of simplifying it down to a final answer.
And this core idea of just cutting out the junk, it isn't unique to this one system. There's a very similar process called cut elimination that exists in other types of logic. Now, the names and the details are a bit different, but the fundamental goal is identical. Get rid of the unnecessary steps to reveal the most direct path to the truth.
So beyond that incredible link to computing, what are some of the deeper implications of being able to do this?
A normal proof gives us some really powerful guarantees. First, there's something called the subformular property, which basically means the proof isn't pulling any weird tricks. Every piece of the argument was already there in the original question.
Second, it ensures harmony, a perfect, elegant balance between the rules for building ideas up and breaking them down. And finally, it helps us define what it means for two proofs to be the same. If two completely different-looking proofs simplify down to the exact same normal form, we know that, in their essence, they are the very same argument.
And I want to leave you with this last thought, because it's a bit of a mind-bender. Normalization is a process of simplification that's supposed to eventually stop, right? But what about arguments that can't be normalized? What about proofs that have loops that just go on forever? Some logicians think this is the very structure of things like the liar's paradox, an argument that can never, ever reach a simple, stable form. It makes you wonder, if the path to truth is simplification, what does an infinitely complex path really represent?